Welcome to the 7th Zienkiewicz lecture. We have people not only in person here, we also have people watching this lecture live. If you don't know me, I am Perumal Nithiyarasu, Associate Dean for Research, Innovation and Impact, Science and Engineering at Swansea University. I also chair Zienkiewicz Lecture Committee. Before I request our Vice Chancellor, Professor Paul Boyle, to introduce the speaker today, I want to say a few words about Professor Zienkiewicz and Zienkiewicz Lecture. Professor Oleg Zienkiewicz was a professor of civil engineering at Swansea University from 1961 until his retirement in the late 80s. In fact, Oleg never retired. I had a chance of working with him in the 90s. He was widely recognized as one of the founders of the finite element method. If you are unaware of what a finite element method is, you may want to Google or ask ChatGPT. Believe me, first thing I did when I enrolled onto ChatGPT was I asked the same question. It gives you a very nice answer for what a finite element method is. The finite element method was one of the essential computational design tools in engineering industries. While finite element was originally developed to understand how aerospace structures work, Oleg was widely credited for taking the finite element method beyond aerospace structures. The work, I remember the preprints of the work in his office. The work was so ahead of time, believe it or not, all society journals rejected the paper. It was finally published in a magazine called The Engineer. Okay, so I'm pretty sure many of us go through the same challenge now. You submit to a journal and the editor often rejects it without external review. It's not new. In fact, he was so frustrated, he ended up starting the first ever numerical methods in engineering journal. Very successful journal. Very good reason to start a journal. If you reject my paper, we'll start a new journal to publish our work. Before handing it over to Paul, I just want to thank a few organizations and people. Swansea University and external sponsorships predominantly support this event. I acknowledge the cash support from South Wales Institute of Engineers Educational Trust and Learned Society of Wales. We have representatives from both these organizations. They have been consistently supporting this event for the last several years. Thank you. Other supporters include EPSRC, the International Association for Computational Mechanics, the Turing Institute, and UK Association for Computational Mechanics. Finally, this event was organized by two excellent colleagues from the Faculty of Science and Engineering executive team, Sam Board and Ruth Colton. They're here. They looked after everything from booking the venue to looking after today's guest speaker and filling the venue with more than 120 participants. A very big thank you to you, Sam and Ruth. With that, I now hand over to Professor Paul Boyle to introduce today's guest speaker.
Noswaitha, and thank you, Arasu, for that introduction, and obviously thank you very much indeed to our speaker for joining us this evening. I'm only going to say a few words briefly just to introduce, because I'm sure you will have all been on the Wikipedia pages and learnt a lot about Lord Darzi already. First of all, though, let me just briefly say a few words. Lord Darzi, of course, is a surgeon, an academic, and to some degree, a politician. He's been heavily involved in politics and advising different governments on what we should be doing around healthcare. He's been involved particularly in innovation and how we might think about putting in place healthcare systems that aren't all about treatment but are about prevention as well. He has goodness knows how many publications. I'm not going to try and guess the number, but I'm pretty sure it must be getting close to 1,000 by now. And, of course, he co-directs the Institute of Global Health Innovation at Imperial College London, and I think holds the Paul Hamlin Chair of Surgery there. So he's an academic, he's an innovator, and he's a politician to a degree in the House of Lords, and somebody who I think is going to give us a really excellent lecture telling us about the innovations that he's developed. We at Swansea, of course, are very proud of our innovation history. We're a university founded by industrialists for industry. And since those very first days, we've been proud of our record of not only hopefully doing brilliant education and brilliant research, but also innovating and spinning out ideas. We rank in the top 5 of the universities in the UK at the moment for spinning out companies which last for at least 3 years. So we have a very strong record in innovation. But I think we'll have a lot to learn from Lord Darzi. We have interests in medical technology here, in both of our science and engineering and indeed our medical faculties, groups of people working on similar areas from quite different perspectives. And we were very proud this week to be able to announce that we've won one of the Queen's anniversary prizes, actually in an area of innovation that overlaps with public health, particularly our SAIL data bank and the work they've been doing over the COVID period. And a particularly nice thing is, of course, that we've won the Queen's Anniversary Prize twice in 2 years, a really rare achievement. And that'll be, that we'll have the celebrations for that early next year. The final thing I wanted to say is we had a great lecture last year as well, organised by Arasu, Jim MacDonald from Strathclyde University, the Vice-Chancellor up there. And the reason I mention that is that Jim came and spoke to us about energy and different energy systems. Today we're going to have a lecture that's about a totally different topic, I suspect, around innovation and healthcare. But it just really demonstrates, I think, the work that Zienkiewicz did and the applicability of that work to such a wide range of different areas. The work that's being done on AI, the work that's being done in the energy systems that Jim mentioned last year, much of that work relies on the methods that Arasu was just talking about. So the breadth of expertise across the world that's come from the early ideas that were forged in this university have been hugely impressive. And I'm really excited to hear about some of the ideas that we're going to hear from Lord Darzi about tonight. So thank you very much indeed, Lord Darzi.
Thank you very much, Vice-Chancellor. Distinguished guests, ladies and gentlemen, good evening, and thank you for having me here with you. It's an honor to have been invited to present to you the Zienkiewicz Lecture for 2023. As we've heard earlier, Professor Zienkiewicz, a British academic of Polish descent, made globally significant and impactful scientific contributions from his august university, or from this august university, in the field of finite element and civil engineering. What made him a unique academic was his passion and desire to share knowledge through his research and teaching activities. In his honor, my talk for this evening is entitled Transforming Healthcare Through Science and Technology, and in some instances, through the major contribution that Zienkiewicz made in his academic career. For centuries, we as doctors have been afforded a most privileged position in society, venerated for our mystical ability to decipher the most complex biology through simply feeling a pulse or listening to a heartbeat. Our powers appeared almost superhuman. The truth is, those powers are superhuman. The biology that defines human health and disease are complex at a scale far beyond the comprehension of a single human being. It is only through science and technology we can hope to deliver a greater health. The COVID-19 pandemic, which we've just heard about, has marked an inflection point in history. Across the world, humanity was humbled as a virus no larger than 50 to 140 nanometer brought societies and economies to halt. Millions died, and years later, we are still learning of the long-term effects of this virus in terms of long COVID. And yet, it could have been worse, much worse. As this chart demonstrates, if COVID-19 had the case fatality rate of MERS and the infectivity of measles, then there would have been hundreds of millions of global deaths within the first 6 months. The pandemic marked another inflection point, the widespread development of novel vaccines in terms of mRNA, which demonstrated the ability of healthcare technologies to harness the power of human biology for the betterment of health. It took 66 days from publishing the COVID-19 genome in the first administration of mRNA vaccine. 66 days. In truth, this feat was the result of decades of tireless dedication by some brilliant scientists. The concept of mRNA therapeutics were discovered back in 1980s. It lay dormant until flagship pioneering and then subsequently BioNTech had the vision to explore its potential as a project that will later become the company Moderna or BioNTech as we know it. After a decade of experimentation, refinement, and private investment of $5 billion, Moderna was able to design a COVID-19 vaccine minutes after receiving that genetic sequence. Not years, not months, minutes. Even more incredible is that mRNA is not a singular success, but a platform technology that has been able to evolve just as the virus has. We have in near real time been able to edit the vaccine to accommodate new variants as we've all been through the different vaccinations we've had. The variant problem would once have been impossible to address if every man, woman, and child alive today were a lab scientist, each of them were doing 1 million experiments every single hour, then it would have taken as long as the universe has existed to test every possible variant of COVID-19. Experimentation is central, as we all know, we're all scientists in this room, to scientific method. At its core, a process of trial and error. What has limited biological sciences has been the seemingly limitless complexity of nature itself. That has been a universal truth, as we all know. Until now. Deep learning and other artificial intelligence techniques, as we've heard from the Vice-Chancellor, are creating a whole new era in biological sciences. When combined with high throughput multi-omics, we are able to organize nature's information to an extent unimaginable even 10 years ago. Just think of the work of Demis Hassabis and DeepMind have done in unfolding the protein, the AlphaFold. The potential impact on human health is enormous. For COVID, the breakthrough was mRNA vaccines, which said to be followed by a new breakthrough, the creation of the first variant-proof vaccine. But what if nature is not the limit? What will we do having harnessed nature's immense power? Well, that's really up to you, up to us as scientists. But here are some of my thoughts on how science and technology will come to transform healthcare as we know it today. We have at our disposal the technologies to understand human biology at every level, from inner workings of a single cells up to how we interact with the world around us. Single-cell omics has given us the power to understand the intracellular pathways of human biology, giving us insight into the health and disease at a depth not even dreamt to be possible previously. This is the approach taken by one company I know, Cellarity, the Boston-based biotech innovation that I've interacted with. Single-cell transcriptomics has been used to identify the cellular drivers that underlay the transition from a state of health towards a state of disease. So you can just imagine that flow. The Cellarity maps they generate gives us as scientists unique insight into these processes, allowing earlier identification of conditions and the possibility of creating treatments that target the aberrant pathways that lead to disease. So could we preempt disease? We are not only gaining deeper understanding of how individual cells are functioning, but broader understanding of how these combine to shape human and health and disease. 1/3 of adults in the UK wear a smartwatch or a fitness tracker. I am wearing one today. We are capturing every step, every heartbeat, every night's sleep, and so much more. The potential is boundless. Since Apple were the first to gain clearance as a medical device to detect atrial fibrillation, the role of smartwatches has been assessed in roles as widely as infection surveillance to monitoring the state of medical conditions such as multiple sclerosis. We at the Institute of Global Health at Imperial are studying the role of smartwatches for guided rehabilitation and pre-habilitation. And that driver came during COVID. Most of our stroke patients weren't getting rehabilitation due to complete shutdown of our physiotherapy departments. In a truly remarkable feat, others have demonstrated that smartwatches are able to accurately predict not only who will develop Parkinson's disease, but when they will. More incredible is the fact that they're able to do so 7 years before they manifest clinically. Improving diagnostics in healthcare is not limited to developing new technologies, but better understanding those we already have. Artificial intelligence will transform existing diagnostics. And again, at the Institute, we have built a deep learning algorithm with DeepMind, which outperforms human radiologists in detecting breast cancer from mammography. We are currently trialing the implementation of this versus a second reader, a human reader, in the NHS workflow. And if successful, this technology will improve the accessibility to mammography while reducing the harms of false positives. Others have applied deep learning to high-burden conditions such as ranging from diabetic retinopathy, as we know, also to chest infections. So building AI into diagnostic pathways promises not only to make these more accurate, but more accessible. AI will allow us to truly democratize diagnostics. Improvements in diagnostics and sensing technology serve to provide us with earlier, more accurate, and more granular diagnosis than ever before. As our ability to recognize disease improves, so too will it be our ability to treat disease with greater precision. In the future, treatments will be tailor-made, targeting the specific cellular pathway with pinpoint precision. Generate Bio, another flagship company, just received its MHRA approval for trials, is using advanced AI techniques to learn the code of nature itself. Rather than discovering existing proteins and what they do, Generate designs new proteins with a specific function. It opens up the possibility of fully programmable medicines that are designed rather than discovered. And it's not just proteins. Generate is able to design antibodies, peptides, and enzymes that never existed in nature. Treatments will not only be made to treat conditions we have, but the conditions we could have in the future. This approach has been taken by another company, a priori, that I've had the privilege of sitting on their board. They are using deep mutational scanning to collapse the variant space, assess the impact on current vaccines, and try to design antibody repertoires that can cover current and future variant of that virus that don't yet exist. That will be the basis for the vaccine of the future. Just imagine a flu vaccine that we received a few weeks ago in October when it was launched that could protect us for this year, next year, and the year after, because we can predict the mutational aspect of that virus. Technology will not only transform the treatments we give, but how we give them. As a surgeon, as the Vice-Chancellor said, who started my career as a failed engineer, by the way, I was supposed to be an engineer, but I rebelled against my father and decided to medicine, and then eventually found the nearest thing was surgery. I continue to practice in the NHS, as you probably know, and I've been in many ways at the forefront of technology. One of the great advantages of being an Imperial, when the merger happened, by the way, many of the physicians wouldn't cross the park. They were the engineers, the scientists. I couldn't really engage with the biologist in Mary's, so I did cross the park, and I developed relationships with them, and really that underpinned all of my scientific collaborations with some amazing scientists and engineers in Imperial main campus. So what we tried to do, could we use technology to reimagine surgery? And what you can see here is the image of a beating heart that has been stabilized by tracking both the movement of the heart and the surgeon's eyes. So we're moving the surgical eyes, looking in the monitor at the same frequency as the beating heart, where you can get a static image. So it means that the heart surgery is less traumatic for patients because it can be done without the need for a risky heart and lung bypass machine. We know the cognitive impact on putting someone on a heart and lung bypass machine. So advances in robotics have seen the next generation of probes that are far more dexterous than even a surgical hand. They enable new frontiers in minimally invasive surgery, allowing fundamentally different way to characterize and treat disease. Here you can see the Da Vinci robot that has revolutionized how we perform surgery. As surgical robotics and augmented reality co-evolve, we will be able to deliver safer and more precise surgery. But bigger is not always better. Imagine micro-robots that are able to autonomously swim through the bloodstream to deliver therapies right where they will have the greatest impact. Or micro-robotics tweezers that are able to grasp a single cell. These are not ideas or science fiction. This is the type of research that is happening in Imperial, in Wales, across the pond, in the US, really at a dramatic pace. Of course, the ability of human biology to recover is finite. So where do we turn when restoring biological function is no longer possible? Once again, science and technology have the answers. Until recently, interacting with our own brains was limited to keystrokes or speech recognition. Having to give physical orders to technologies we interact with. But what happens as the interface becomes seamless? When the technologies we interact with are controlled by our own thoughts alone. Again, scientists in many universities in the UK, including Imperial, are developing technologies with the capability to read these signals directly from a nerve cell. And imagine when those signals are not sent to a computer or to an external robot, but to an artificial muscles implanted into a human body, artificial muscles that respond to electrical stimuli just as our muscles do. Once again, this technology is not an idea for the future, but a reality today. As we combine these, we will have a closed loop that perfectly mimics human functioning. Physical disabilities may be relegated to history books as people are given the ability to walk again. So the benefits of these technologies will not be limited to the unfortunate few. Take sarcopenia. Age-related muscle loss will affect every one of us in the later part of life. It need no longer limit how we live and engage with society. As I said at the start of the talk, we stand at an inflection point in the history of healthcare, a point where science and technology has given us the tools to deliver better health for all. So I say to you, welcome to the biological era. The technologies we have discussed this evening are each an incredible feat of science. On their own, each has the potential to improve patient lives. Imagine what healthcare would look like when these technologies work in concert. But unless we transform our healthcare systems, the uptake of all of these innovations will be slow. Patients will miss out. People will live in sickness when they could live in health. We need not only develop new technologies for healthcare, but develop a healthcare system that embraces these technologies to deliver greater health. Developing healthcare technologies is difficult. Changing healthcare service delivery is nearly impossible. The basic structure of our health system hasn't changed much in 900 years or so. This is a picture of St. Bart's Hospital in London, which I'm sure some of you will recognize. The founders of St. Bart's in 1123 would not have recognized modern medicine. But I promise you, they would have found the pattern of service delivery today all too familiar. We wait until we feel sick, until we have a symptom. We then go and see the doctor, usually a GP, working in their offices. And then, if we are seriously unwell, we go to a hospital. It's pretty much the same pattern as it was in 1123. NHS reforms, Vice Chancellor said, I did join the devil for a few years, have always focused too much on changing management or incremental gains rather than changing care delivery. You will never appreciate the value creation of a technology unless you change the delivery. But the current paths have reached the limits of sustainability. This chart is based on US data. It shows that the world's largest economy is set to dedicate a third of its GDP to healthcare by 2050, a third. For the UK, we can expect to be spending around 20% of our GDP on health, nearly double what we are spending today. The problem is that most health systems struggle to kick their bad habits. These are the 7 bad habits of health systems, which I had the privilege of developing as part of the World Economic Forum in Davos many years ago. Healthcare systems focus on sickness, not health. They focus on quantity, not quality. No matter the evidence, the status quo tends to prevail. Innovation is stifled. The focus is on inputs, not outcomes. They're even dragging universities into that. Vast quantities of data rarely translate to insight or action. And there is a persistent failure to take responsibility. Imagination is essential to innovation, and everyone in this room is imaginative in what they do, whether that's in their academic practice. The first step is to create a new future, is to imagine it. To ask the question, what if? So what if we invested as much in keeping people healthy as treating them when they are sick? Just a thought. We currently think about our health in two states, that people are either healthy or they are sick. In fact, there is a period of time between being healthy and becoming symptomatically sick. When physiological changes are underway in our bodies that put us on a trajectory towards disease, but what we do not yet have are symptoms. We call this period, by the way, a pre-disease state. It's defined well in certain diseases, but not in all. So what if the technologies we have discussed this evening have the potential to recognize these pre-disease states? What if the technologies we have discussed tonight have the potential to stop, slow, or even reverse the transition towards disease? What if health status can be maintained and disease states can be averted? If we can preempt disease, then we can stop people from becoming patients in the first place. And I believe in the biological era can herald a whole new era of what I describe as preemptive medicine, where we can consign disease to history, where healthcare adds life to our years as well as years to our lives, where we think about our health span as much as our lifespan. What if implantables or wearable sensors could detect pre-disease? In other words, you no symptoms yet, but something that triggers you and say, you better do something about this because you are on a trajectory to disease. Imagine a world where our health is continuously and passively monitored. Imagine a world in which sensitive diagnostic technologies can be accessed from the comfort of your home or in your local community. That rather than waiting for symptoms of sickness, we would find out that we were heading towards disease at a time when something could be done about it. And now imagine that rather than having to go to the GP surgery or to the hospital, most interventions could be delivered safely to us at home. A world of digital therapeutics and treatments that could be delivered directly to us, where we could monitor our present and future health through an app or a phone. That's the future of healthcare delivery. Technology means we can reimagine healthcare. It means more of our lives spent in health rather than in sickness. More time to live, to work, to study, to spend with our loved ones. Time itself is the promise of the future of healthcare. Welcome to a world liberated from disease, and thank you.
Thank you for the talk. Very enlightening, I must say. Some of the examples that you provided on the future of AI in medicine, I was thinking it's a lot of utopian view that you have, which is more about the utility of AI in healthcare. But I was considering what could be the downside or the dystopian view in the perspective of healthcare when it comes to AI applications. Like, for example, you talked about antibiotics, patterns, proteins. How do you feel we could be it could be more beneficial, but at the same time, it could have that responsibility and other aspects to it.
It's a great point. It worries me. It worries many of us in this room. It worries even the AI scientists, by the way, who spend a lot of time and effort in doing that. And I think the other thing which we don't know is how do we regulate this? Because history has shown us that we either over-regulate or under-regulate. We never get this right. And that's why we had the recent summit, as you know, hosted by the Prime Minister, which it was a bit of a jamboree, but I think there was at least a debate about how we engage in AI. I mean, the regulatory framework is fascinating, as you may know. We've decided there will be a single regulator that looks at AI of all disciplines, where there's a way of looking at that. And probably we've done that because I don't think we have that expertise to go on a vertical levels in each. I mean, healthcare in itself is a huge space, where the US have taken completely the opposite view. I think the biggest concern is, well, let's start by developing the algorithms. The big concern, and I've seen some of this, by the way, is it could actually make the inequalities even greater, because most of these images that we're reading are not necessarily representative of our societal diversity. That is a serious issue, and I think the regulators need to take that very, very, I think the inequalities issue are a real concern to me. Obviously, there's the issue about privacy and all of that, but I think we can manage that reasonably well. So there are the threats. The opportunities we have in this country, I mean, whether Bevan, being in Wales now, did predict that 75 years later, his single payer system and a single medical record will yield the biggest return on any healthcare investment in terms of AI. Maybe he did. What did he say? If the pan drops in a ward in Wales, he will hear it in Whitehall, if you remember that. So we have an amazing asset. We have a single medical record. If we can get our act together, if we can really improve the quality, by the way, we do talk about this, but the quality of the data is questionable in certain areas. If we can improve that, we have an amazing asset fuel in terms of really driving some amazing algorithms in delivery. As I've described to you, the potential, again, coming back to a single-payer system, the potential to preempting disease, not public health, actually preempting, risk stratifying population, because we have records from the cradle to the grave, as we all know, we potentially could create huge opportunities for a single-payer system as we are today. So I've described both for you, but the inequalities are the big concern I have. There's many other concerns, as you probably would have heard about and read about. There's also scaremongering going on as well. You know, when robots came in, I had the same story at the time. Robots are going to operate on you. The surgeons will be parked on the side, but nonsense. Yeah.
Thank you. Next question.
Hi, Prof. Saeed Ashraf, consultant cardiothoracic surgeon. Okay. Yes, we know it is a future in our medicine, but only one thing gets me worried about. At present, AI, to my understanding, is a data dependent.
Yeah.
And our cardiovascular data is such a microsecond changes because of the biochemical changes in pathways. Do you think this data confirmation and implementation will affect our valve surgery, coronary bypass graft operation, and all those things, which is the bread and butter at present, anyone above 40 or 45 years of age?
Could it predict people who need coronary artery bypass graft? Is that what?
Any disease related, because it changes so frequently in our biochemical markers.
Yes, I mean, at the end of the day, what the AI does, which a human being cannot do, is to look at the trends in massive data sets in which you can actually start eventually learning what the prediction pathways might be. So, yes, I mean, we still haven't, no one has published anything about that on, continual change, but there's plenty of evidence in other sectors it could definitely happen. I mean, managing the electricity grid in this country now is run on an AI machine. And there are certain bits of it which you can predict. You know, at night time when people are going to bed, they're going to switch on the electricity, the demand is going to reduce. But there are certain surges that manages, and I've no doubt cardiovascular disease will have certain surges in demand that could actually strain the heart, and you can find ways of measuring that and predicting that in advance. Whether that is, I don't know, are trying to get into as being a diagnostic tool in picking up people earlier. Yes, you can. I mean, imaging might pick it up, but I'm sure there will be some biomarker in years to come with AI discovery that could pick up pre-disease states rather than a coronary artery angiogram done in an MRI machine or an MR angiography of the or CT angiography of the cardiovascular system.
To predict that one.
Yeah.
Okay.
Thank you. Thank you.
So you're uniquely placed, Lord Darzi, with your political and medical and engineering background. Are you an optimist? Are we going to get to this new health system?
I'm an optimist, absolutely. I mean, listen, I don't think I could remember ever since I've arrived here, by the way. You may know, I got to London in 1990. I was in Ireland, that's where I did medical school. And I am an optimist, absolutely. I mean, it's not worth living if you're not one, not in the NHS or the National Health Service. So, yes.
Khaled Almana from Swansea University. First off, I would like to thank you, Lord Darzi, for the lecture. It was very enlightening. My question is, how do you think AI would be integrated in the future into genetic engineering and gene therapy, and would it be possible to reverse or cure genetic disorders?
Absolutely. I mean, to be fair, we could do that now without AI, but let me just say, it's already happening. I mean, this is not something that's going to happen next week or next month. You just cross the pond, you know, AI, drug discovery is becoming the norm. You just have to go now to, what's this new company set up by DeepMind? It'll come to me. That is happening. You know, I mean, I'm now leading a big initiative around the centenary of the discovery of penicillin by Alexander Fleming, which actually is in St. Mary's. It's about sort of 2-minute walk from my office. And we're looking at AI in new antibiotic discovery. I mean, there are millions of assets sitting on big pharma and other institutions and academic institutions, the ability to screen those and come up with some new antibiotics that we're not resistant to. That is happening today. The ability, diagnostics, by the way, improving the speed and acceleration of diagnostics. And I'll envisage you know now, this is 2023. It's a scandal, this whole antibiotic prescribing. 2023, you still don't know when you prescribe someone antibiotics whether they have a viral cold or they have a bacterial infection. It's just amazing. We have to sort this out. You know, antimicrobial resistance is a human creation. It's the misuse and overuse of antibiotics. So the potential of introducing AI, even on your mobile phone, that could send an image and do some analysis, get back to you, is the way forward. So all of this is happening, and if you predict it's going to happen in 10 years, it's probably going to happen in a year. I mean, I've presented to you generate all the protein. That is all AI-driven. A priori, identifying every possible variant 10 to the power of 50. That's a huge number. And able to pick up that virus and predict every possible mutation. By the way, they predicted sort of probably the sister of Omicron during COVID. AI predicted that because of it didn't predict as many switches when Omicron what happened. I think there were, can't remember the exact number, but that is happening. That is currently happening. It's going to disrupt big pharma, by the way. It's going to improve access to therapeutics and diagnostics.
Thank you.
Don't wait. Join the boat.
Can I hog the microphone for a second from the back here? So I'm an exercise scientist, Lord Darzi, and I'm really interested in your work with smartwatches.
Yeah.
So what do you think the future is for smartwatches, and how that may feed into a whole system about wellness in particular, as opposed to illness, as you just mentioned?
I mean, I don't have I haven't done a horizon scanning with it, but I could tell you I am one of those who have a smartwatch, and I have something else that measures my sleep, and I wake up in the morning with a degree of anxiety before I see how well I slept, whether it's a yellow line, whether it's a red line, whether it's a green line, and that actually makes me feel worse than I thought I might feel if I did not know that. So the answer to your question is it's very open. There is a lot of, at some stage this will improve. I would love this thing to tell me why is it yellow in the morning rather than red or rather than green. It doesn't talk to me. So at some stage we will find a way of addressing that. So I do it, but you know, it's all to do how we're going to get. I think we are on a trajectory to get there, but as it stands, I don't think it's going to have a big impact. But I think the future it would definitely.
I've got one, thank you very much, thank you. I'm Rhiannon Owen, I'm Professor of Statistics at Swansea University, but I also sit on the NICE Technology Appraisal Committee as an NHS decision maker and reimbursement. And it was really enlightening to hear your kind of thoughts on the regulation process and what the regulatory bodies need to consider. Do you have any thoughts on what the sort of reimbursement agencies need to consider and how we start to embed some of these artificial intelligence and machine learning techniques to appropriately assess what happens, and in particular, I guess, thinking about things like companion diagnostics? Yeah,
absolutely. So, great question. I could spend all day talking to you about this. I mean, let me just praise there's two of them. We should be very proud of MHRA. I think our regulator has really, during COVID and since COVID, probably been described as one of the greatest innovative regulator in the world, actually. And it's fascinating to see what's happening in the US. Many startup companies are coming to the UK to get an approval because there is a deal between FDA and MHRA. If you come through MHRA and get your approval, do a study there, you can go back and go through the FDA without an approval. So we should congratulate, I mean, that's an amazing, I mean, their behavior during COVID was phenomenal, absolutely. Have you come across June Rain? She's brilliant, absolutely fantastic. NICE is sort of lost its way to a degree on the appraisal sides. NICE is the one that I remember probably had the biggest political interference when it comes to qualities and cost and all of that. And I think that needs a serious reform. I don't think they are ready to address these issues of AI. You know, technology to survive, we all know this, it has to improve, it has to have a health gain. And to be disruptive, it has to be cheaper. It has to be more of masses. And AI is that type of thing, no question in my mind. Preemptive health, public health is proven historically, by the way. I mean, who is the greatest innovator in public health? It was Queen Victoria. You know, she introduced sanitation, clean water, all of that. She is the one who extended human life more than any other public health doctor I've seen, with the obviously, excluding some who might be sitting in this room. So public health has been a dramatic. I mean, life expectancy doubled in 1 century, up to the millennium. The question is, what is this millennium going to look like? Is going to be phenomenal. I think extending life alone, we're coming to the conclusion as we reach 2025, passing the quarter of this millennium, is that we seem to have ignored one other thing, is adding years to life is one thing, but adding life to these years is another thing. And that is what NICE and MHRA should start thinking and managing. Technology will help, I have no doubt. And that is where this whole idea of preempting disease comes in. There's no point, you know, all our health systems are sickness services. We have to find another way of preempting a sickness before it manifested, because if you can intervene, as in public health, you can actually treat that condition.
So we're moving towards the end of this section. Maybe time for one more question. Did you want to ask a question?
I have the mic. Well, I share your optimism, but I have a question about trust. You know, trusting machine to do mammography, to do robotic surgery, is not that complex to conceive. But can we trust, you were talking about the unique medical record in the UK, which is fantastic, but can we trust Palantir, Palantir, you know, Thiel company to manage the data? How do we trust people? Who do we trust?
It's a good point, and I'm sure it concerns the public, and I sympathize with those who do. At the end of the day, all is how do you manage risk, and having private sector firms holding the data, as long as it's a very clear regulatory framework to regulate this, and making sure that the citizen of this country sleeps well at night thinking that their data is not being tinkered with. Trust means a lot of other things, by the way. This is what you're talking about. What I'm talking about is confidentiality, is very different than trust. Trust implies that whoever is holding the data has some nasty motive to kill you or get rid of you or put an implant in your head who starts behaving weird. That's not what I'm talking about. So, yes, I mean, there's risk in everything we do. How do you manage that risk? I have no idea. I've read the newspapers about the new recent procurement of Palantir and with their history of military use and all of that. But, I think all of us will have our own private views about that. But I do go to sleep thinking that there's a good regulator out there. And actually, a regulator that has a track record in this. They have really gone out and punished you, as you may know, historically, in this country more than the US has. So we're a little bit more on top of it than the US.
Thank you very much indeed, Darzi. Thank you all for asking the questions.